5 minutes, so we will run a little bit late, is a bit more mathematics. Just to warn you, it's a bit more mathematics, but I try to do my very best to use, I use a lot of graphics, but also some formulas. So it's topological data analysis. It's a special kind of analysis that not every data guy is aware about, and some quantum aspects. So the agenda is I introduce something that's called homology. Right? And based on homology, I introduce something called Betti numbers. We are now deep in topology, and you use topology to turn point sets into topological objects, and then you can analyze the topological aspect, what are the noise of the data, very nicely. So this will be 35 minutes, this will be only 10 minutes. And then summary. So, homology. What the hell is homology? This is one of the simplest right now. So, what I have here is you have a bunch of points, n+1 points in a space, and the points are such a case that you have a base point P0, and P1 minus P0, P2 minus P0 must be linear independent. So they are not in the same line, they are linear independent. This is called affine independent. So you have a bunch of points, these are 3 points here, this is the base point, and the two vectors are linear independent. And then these vectors, these vectors span a complex hull. So the points are basically used to compute these linear combinations. The coefficients are greater than 0, sum up to 1. So what this basically is the inner part of these vectors. This is then called a simplex, an n-dimensional simplex of dimension. And the points are called the vertices of this simplex. And if you have subsets of the points, you create so-called faces. One-dimensional faces are edges, zero-dimensional are the vertices. Here are simple examples. So Sn is the set of all n simplexes. The zero simplex is just a point. Simple. And one simplex is a straight line. A two simplex is a filled triangle. It has dimension 2. And you have a tetrahedron that is it's a filled tetrahedron. It has 4 triangles that's of boundary, and the inner part does also belong to it. Very simple. Complicated definition, but absolutely simple. Simplexes. Then you collect simplices of different dimensions. Then you get the so-called simplicial complex of dimension n, that basically is for each simplex in this simplicial complex, the face, the edges, the nodes, and so on, they are also part of the simplicial complex. So you'll see it in the example. If you intersect two simplexes of a complex, the intersection is again a simplex or a common face of both simplexes that you do intersect. And S contains at least an n-dimensional simplicial complex, because we say it's a simplicial complex of dimension n. So this is a simplicial complex. Right? Here you have a 3 simplex, a 2 simplex, a 1 simplex, and they all intersect nicely and so on. The simplicial complex. Right? Like some toys, Lego, block, and so on. This is not a simplicial complex. It's not a simplicial complex because these triangles intersect, but the intersection is not a common face. It's only a part of it. These intersect, but the intersection is a point, which is not a face of this triangle. Right? So this is badly formed. This is not a simplicial complex. Then, out of simplexes, you can build a so-called chain. Right? What the hell is a chain? You have a bunch of simplexes. These are simplexes of dimension p, to explain that. And then you need a field, like Körper in Deutsch, like the real numbers or complex numbers. But here we need a very special field, the field Z2, consisting only of 0 and 1, with addition modulo 2. That is 0 plus 1 plus 1 is 2, modulo 2 is 0. Right? This is our field. Then you do something absolutely strange. You take these geometric objects, sigma I, and you multiply them with a number. It means nothing. You multiply them with a number and you add them up. It's an abstract thing right? It's a geometric object with a number and a sum. And this is then called the P chain because the simplexes have dimension P. And then you can add these P chains. You can multiply the P chains with numbers. Very simple. You add two P chains by adding the coefficients, right? You multiply them by multiplying each of the coefficients with the number B. And if you do that, you get a vector space. You get a vector space of P chains. So we have some very formal abstract thing, but we get something everybody is used to, a vector space. And you can compute this vector space. That's already good. And this thing is then called CP, the set of chains, the CP that are contained, the P chains contained in this simplification complex, and we leave out S if it's clear what S basically is. And then you have a fundamental operator there, the so-called boundary operator. The boundary operator maps a P chain, a chain that consists of P simplexes, to simplexes of one dimension lower. How do we do it? We take a look at the simplex, that is the convex hull of these points, and you compute the boundary by leaving out one node after the other. Right? And then take a look what the hell basically, you will see examples of it. And if you have a complete chain, the boundary of the chain is where you take the boundary of the composing simplexes here. Very simple. And this partial P is the P boundary map or boundary operator, and if P is obvious, you omit it in, only write partial. And the result of applying the boundary operator to a simplex is called the boundary of the simplex. Here are examples. The boundary of a point is not the empty set, it's 0. 0 is the neutral element in the field. The boundary of this one simplex is, this is not geometrically defined, the endpoints of the line. The boundary of the filled triangle is only, the boundary of the triangle, right, the 3 lines. The boundary of the tetrahedron are only the 4 triangles, right, that are there, but the inner is then gone. This is the boundary operator. Now we compute something. I have here a filled triangle. I want to compute now the boundary of this filled triangle. So what I'm doing is the boundary of the ABC is the triangle. The boundaries, I omit the C, I get AB. I omit the B, I get AC. I omit the A, I get BC. And I need to add them up. Yeah, very simple. It's a formal operation. We play with symbols here. This is this piece. And obviously, yes, this is the boundary. I would ask what is the boundary. You will say this edge, this edge, this edge. Yeah, this is simple. Now I compute the boundary of this boundary. So what I do is, the boundary, the 2 boundary is this thing here. I apply now the 1 boundary to this thing. So that means I omit B, I result in A, I omit A, it results in B, I omit C, it results in A, and so on. I get this formal sum here. Now I rearrange it, it's A plus A, plus B plus B, plus B plus C, but this is then 1 plus 1A, 1 plus 1B, 1 plus 1. Now 1 plus 1 in Z2 is 0, because 1 plus 1 modulo 2 is 0. Very good, you passed. So that means here, this is 0, that means the boundary of a boundary is always 0. What a surprise. And this is an inherent fundamental feature, right, that the boundary of a boundary is always 0. Here, we are over, we learned it, thank you very much. So, this is only the beginning. So, now you have an operator here, a linear operator, where the image of the boundary of a boundary is 0. That means what I do is this following. The image of this boundary operator is in the kernel of this operator. In mathematics and linear algebra, the kernel of a linear map is the set of all vectors that are mapped to 0. Because if I take the boundary of the P simplexes and then I apply the boundary operator again, they are always 0, as we said before. Boundary of boundary is 0. That means the image of partial P is in the kernel of partial P minus 1. Right? And this means, so I call a P minus 1 chain a boundary if this p minus 1 chain tau is the boundary of a p chain sigma. This is the boundary. That means tau is in the image of the boundary operator. A chain that has a vanishing boundary is called a cycle. You will see why it's called a cycle soon. Right? That means a cycle is always in the kernel of this operator, of this boundary operator. And we call two cycles, sigma, sigma hat, homologous if they both are the boundary of a higher dimensional simplex. That's tau is the sum of sigma and sigma hat. If this is the boundary of the next higher dimensional simplex phi, they are called homologous. Right? What that means, geometrically means, comes next. Right? And so that basically means cycles, sigma and sigma hat, are in the same homology class because both are in the kernel, because cycles are always mapped to 0 because they are in the kernel, and that basically means because sigma can be written as sigma hat plus a higher level simplex, right? If you take a look at this composition, the cohesion space, this is a vector space, this is a vector space. If you take the cohesion space, that means a member here consists out of all elements that only distinguish by an additional tau that is in the image. You see an example that's much simpler. So, and homology can be used to find holes in geometric structures. Here's a geometric, so it's a simplicial complex. What I do is, if I compute the boundary, right, it is a plus b, which is not 0. Right? If you perform the computations 2 slides ago, the computer again, you get out these two nodes here. So there is no cycle. Sigma 1 is not in the kernel of a boundary operator because the boundary operator maps sigma 1 to something not 0. That means this geometric thing does not contribute to any homology. No cycles are there. If you take a look at this thing, we computed it 5 minutes ago. The boundary operator is 0. That means there is a cycle, and the cycle indicates the hole, the white space between the edges here. Sigma 2 is in the kernel because sigma 2 is mapped to 0. Sigma 2 is not 0. That means it contributes to the homology. There is a hole inside. If you take this thing here, the filled triangle, although there is obviously sigma 2, the boundary is a cycle, there is no hole because the inner of the triangle fills the hole. Right? You can compute that. The boundary of sigma 2 is 0, and it is the boundary of this tau, so sigma 2 is not a hole. Blah, 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 blah. Here's now a real example. I have this simplicial complex, and what I do is I compute the boundary. I leave out f, I get a b, I leave out b, I get a f, and so on. This is here the sum that you can compute if you believe me. What I will then do, all pairs that appear twice are mapped to 0, because if 1 plus 1 is 0, and so on. So what remains is this thing here, and the arrangement is done by will, because if you take a look at this thing here, this is the orange cycle, this is the purple cycle. So this is basically, if I compute now, the boundary of this thing is 0, and of course the boundary of this thing is also 0. That means both are one cycles. This is a one-dimensional cycle, this is a one-dimensional cycle. That means this is the one boundary of this two-dimensional thing. That basically means they are homologous. The orange thing and the purple thing are homologous. Very abstract. When I heard that many decades ago in my math studies, that this is bullshit, because I love something different called homotopy theory.
We count the holes.
Huh?
We count the holes.
Yeah, yes, we count the hole.
How many holes? We count that.
Yeah, we counted that. We can count the hole. Good question. So if you want to find out, the topological structure, what are the holes in a set in space, you need to map that to a simplicial complex. This is called a triangulation. Triangulation is you have a simplicial complex and you have a very fine map called a homomorphism. It's like a deformation, if everything is made out of gum, right, you can deform it without tearing it apart. This is a homeomorphism. But you squeeze it, you tear it a little bit without disrupting it. Right? This is here a triangulation of this thing. This can be better understood. This is a disk with a hole inside there. Right? This is a triangulation. And we saw before, homology, that this outer purple thing, this is the orange thing, and inner is this purple thing, right? This is the triangulation, and you see here some cycles. But in homology, you only measure this abstract thing with fields and vector spaces, blah, blah, blah. It's better to comprehend if you take a look at homotopy. How can you deform continuously one thing to the other? Homology is doing some algebra, but homotopy is what I do in my brain. You can deform stuff. So I deform it now, right? I take the orange thing, I shrink it and shrink it and shrink it. So the orange thing could be shrunken to the purple thing. Right? The orange thing, because it is filled here. This is filled, right? Within the points I can shrink it. And that basically means that homologous cycles can be deformed into each other within the chain, within this gray thing. Right? So, and homologous cycles indicate holes that do not disappear by continuous deformation. So homology is an algebraic thing. You can compute holes, and topologists, they take a look and see the holes. But we are computer scientists, we want to compute, we want to find out whether we can compute the holes. This is why I introduced homology. Here we have the two sphere, the Bloch sphere, right? Each closed curve on the sphere can be contracted to a single point. If you take a rubber band on the football, the rubber band can shrink into a point. So there's no two-dimensional sphere. But the interior of the hole, the interior of the sphere will not vanish. There is a hole, the void within the sphere. This is a hole. There's no two-dimensional hole, but a three-dimensional hole, the air within the football. So, and here's the torus. Right? You have the purple line and the yellow line. The yellow may be not well seen from the background. The torus has two-dimensional holes because the purple thing can't be contracted to a point. Whatever you try, the most you can get, you can shrink the purple thing to the inner circle here. And this yellow thing can only be moved around; it will never go away. Well, the torus has two-dimensional holes, and of course the interior, the void. That is also the void. It is one three-dimensional hole. So what we now do is, we come back to these examples. If you have an nth simplicial complex, you have many dimensional simplices in there. You can have this chain here, right? You map this here to compute the boundary here. So this is a chain. This is unfortunately also called a chain complex. It has nothing to do with the simplicial complex. It's a complicated structure of maps. It's called a chain complex. And as I indicated before, if this is a vector space and this is a vector space, in linear algebra we learn that the image and the kernel are vector spaces. If you have vector spaces, you can take the quotient vector space, right? It's again a vector space. And the dimension of this vector space is what is called the Betti number. Well, the Betti number is the dimension of this vector space. This is the Betti number of a simplicial complex, the P Betti number. Right? And often, only the additive structure of this vector space is of interest, so people speak about the homology group, because they don't care about multiplying the numbers, only the additive structure is relevant. This is called the homology group, and the Betti numbers is counting the P plus one-dimensional holes. And we can compute them with algebraic means. This is why it's so of interest of computer scientists if we want to analyze data. And P0 is the number of connected components. Now examples. We saw that before. The sphere is connected, so the zero Betti number is 1. It has no two-dimensional holes because any rubber band can be contracted to a point. It has one three-dimensional hole, the interior, the void. These are the Betti numbers. If we take a look to the torus, we said it's connected. Betti 0 is 1. Betti 1, we have two-dimensional holes here and one void. Betty 2 is 1. That what we saw before. It is connected. It is one two-dimensional hole, but no three-dimensional hole. It means Betty 2 is 0. So it seems to be, and this is at the heart of topology, that the tuple of all Betty numbers are characteristic for a set. Completely up to deformation, the set of Betty numbers determines what it is. I can blow it up, I can shrink it, but the holes inside or on top of it will never change. This is a topological characteristic of a space. So how do you compute that, the Betty numbers? If you have a linear map between two vector spaces, if you remember what that means is you can turn a linear map into a matrix. All you need to do is you need to fix bases. You fix the basis of the origin vector space and the basis of the target vector space. I assume the alphas are the basis of this vector space, the taus are the basis of this vector space, and then you can come up with a matrix, right? To find out what is the image of the basis vector A alpha I as linear combination of the base vectors the taus. Right? This is the basis. Here this is called the boundary matrix because it is the matrix of the boundary map. Right? Blah, blah, blah. And then to compute the boundaries of any simplex, right? If you have a chain C and if you want to compute the boundary, then this is what you do, and this is exactly matrix multiplication, as we learned in linear algebra. If you have a matrix, you take a vector and multiply it, and then you get the image of the vector. And then you can introduce something that's called the Smith normal form, not to be confused with the Schmidt normal form that you have a tensor product, Schmidt strength, blah, blah. It's the Smith normal form. And it says if you have a rectangular matrix, and we make this rectangular, it's not zero, right? You find non-singular matrices A and B so that you can transform the matrix into this very nice shape here. Here the numbers are integer numbers, one is the divisor of the other, very nice form. And furthermore, if the field is Z2, then all the m's are 1. This can be easily computed. What you do now is you compute the Betty number of this boundary matrix, right? And then you see the columns that have a 1, exactly 1 in them, determine the dimension of the image, and the columns that are all 0 are the dimension of the kernel. And you need to compute the dimension of the quotient vector space. That means you take the dimension of the kernel of partially 1 minus this one, then you have the Betty number. That basically means you need to compute two matrices and then you can compute the Betty numbers. Complexity is cubical, so it can be done, right? Compute the dimensions here. But the assumption behind this algorithm is that the simplicial complexes are given by the list of simplexes, which is not at all true in practice. You have only the points, or the highest dimensional simplexes. This will make things complicated. Right? In practice, this is not the case. And the complexity in the classical case is to compute the kth Betty number of a set of points is in classical algebra is exponential, either in the number of simplex or in the number k of the dimension. Right? And the classical algorithms need exponential compute time to compute all Betty numbers, but we need all Betty numbers to understand the inner structure, the topology of a point set. And it's even NP hard if you only have the points of the simplicial complex. So it's a known NP hard problem. But there is a little bit alternative computation. You can take this boundary matrices and it's transposed, and the lower dimensional boundary matrix and is composed to multiply. Then you get something that is called the Laplace matrix of a graph, right? It's the combinatorial Laplace matrix. And then you have a deep theorem in algebraic topology that the Betty number is the dimension of the kernel of this Laplace matrix. It's called the Hodge theorem. Deep and complicated theorem. That means that, and this kernel, everything is mapped to 0, is the eigenspace of the eigenvalue 0. Like the kernel, every point in the kernel is mapped to 0. That means the vector times 0 is 0. That means 0 is an eigenvalue. All vectors that in the kernel are the eigenspace of the eigenvalue 0. Right? That means the dimension of the eigenspace is the multiplicity of the eigenvalue. And I mentioned before that what quantum computers can do is computing eigenvalues. Now we come to quantum computers. Right? So computing multiplicity means to compute the Bethe numbers. The Bethe numbers can be computed as the eigenvalues and so on. Then there has been an algorithm 10 years ago by a person who is very famous in inventing new algorithms called the QTDA algorithm, the Quantum Topological Database algorithm. He came up with an exponential speed up to compute all Bethe numbers of a point set. But, so it's an exponential speed up, but he requires something that is called QROM, Quantum Random Access Memory. This is known that nobody can build it and will build it. So it's a theoretical assumption. This kind of memory cannot be built. Even if you ask vendors, they say it would be very nice, but we can't build it. It's too hard, too difficult, too many technological problems. And the algorithm is based on computing eigenvalues based on an algorithm called quantum phase estimation. It's an algorithm that requires noise-free quantum probabilities which are not there yet, error-corrected compute. And yet a few years later, a group from IBM, it was 21, 5 years later, came up with an algorithm that can do topological data analysis on today's machines. They compute all Bethe numbers also with exponential speed up with a nearly linear algorithm, and even a better speed up. And while the Lloyd algorithm uses the Grover algorithm, it requires error-corrected QPU. It requires QPE, as I said before. It requires the error-corrected QPU. The IBM algorithm basically needs neither Grover nor QPE. That basically it can run on today's machine, and they showed that with high-dimensional simulation complexes. Blah, 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 blah. Then I mentioned before, whenever a new quantum algorithm is published that is faster, exponentially faster than the classical one, the classical computer scientists go crazy and want to invent a better classical algorithm. So, and then the quantum algorithm guys, they try to say, no, it's not possible, by proving that you can't build a non-exponential classical algorithm. And they do it as follows, for example. I need to introduce, there's a very lightweight quantum computation model called DQC1. DQC1 basically means the following. You have a single error-free qubit, and the rest of the qubits can be noise-free. Can be noisy, can be error-prone. And here's the algorithm, and all you need to do is you need to measure the error-free qubit, and this error-free qubit, this 0 or 1, gives you the result of the algorithm. Right? So a single pure qubit suffices, and you need an arbitrary number of noisy qubits. It's very weak prerequisite in practice for quantum advantage. And you can prove that there is already a very simple class of these DQC1 algorithms solve many classical problems with exponential speed up. Here's an example. I don't dive deeper into that, right? Computing the trace of a unitary operator can be done in polynomial time, right? And the question is, can you classically, efficiently simulate classically a DQC1 algorithm? And the answer is, surprisingly, under the assumption that pH does not collapse, the polynomial hierarchy does not collapse, with many people think it does not, right? You can prove that this DQC1 algorithm cannot be simulated classically. It means if you can prove that the quantum algorithm is DQC1 complete, it cannot be classically be solved faster than exponential. And one of the problems is called low-lying spectral density problem. You should compute the number of eigenvalues below a given threshold. Right? That means if you put the threshold close to 0, you compute all the eigenvalues of dimension, the number of eigenvalues that are 0. Right? So the Bethe numbers. right? Computation low-lying, this is DQC hard, you can prove that, right? It has been proven. And the computation of this low-lying spectral density computes the Betti numbers. The input is the Laplace matrix, right? And computing Betti numbers is DQC1 hard. And we have an algorithm that can solve it in polynomial time. The open question is whether you can prove that even for the restricted case of Laplace matrices, this is DQC1 hard. It is hard for all matrices, but it's not yet known that it is only for Laplacian DQC1 hard. But there are many indicators. We had 3 years with a colleague from Leymann who said he was a computer algorithmic guy. He said, in a couple of years I believed it can be proven. Now I'm not so sure. I had a phone call 4-6 weeks ago. And he said, I'm absolutely sure there are groups that are making a lot of progress. We will prove it in the next few months. So if we prove that, then you can prove that Betti numbers cannot be computed classically efficiently. That means that would be a non-dequantization problem. Yeah. So now I have 10 more minutes. Okay. Good. Simplification complex and concepts. Now we want to do data analysis. We want to have data that are living in some space, and we want to compute the Betti numbers. We want to find out what is noise and so on. So how do we come from point sets to simplification complexes? It's very easy. We have a point of the point set. We take a radius r, and we take the disk around the radius. This is the ball around x of radius r. And then if I have 3 points, I take radii, fixed radius r, they don't intersect, it's still a discrete set of points. If I increase the radius a little bit, so that these two disks are intersecting, then I draw a line between the 2 points. But this disk does not intersect with the other, it remains isolated. I increase the radii again. So what I do is now this disk is also intersecting with this disk here. I add a second edge here. If I increase further, right, all 3 are pairwise intersecting. I have this full triangle. If I would have decreased even further, I can fill the triangle. So here's it again. What I did here, this is a point set. I've chosen a certain radius. Then I get this configuration of this in the intersection. This is this simplification complex. And it has one 2-dimensional whole, it has 2 connected components, right? It has no cycle, because every hole is basically, it has no void, because this is also fit. So then you can compute Betti numbers of these point sets.
But what if I further extend it?
Yeah, absolutely. Yeah.
Because this is not unique, no?
Absolutely, absolutely not.
Okay.
And we do further extend it, and if we do it, we build something called the check complex. Check mathematician. So here you have the points of data. You take the disks around each data point of radius r, the balls here around x, and then you build the check complex as I outlined before. Namely, if you take a subset of the point sets and the disks of which are intersecting, you add the corresponding simplex to your check complex. Then, if you have a simplex in the complex, right, and you take a subset of the points that you say, then blah blah blah. This is exactly what I said before. And this gamma xr is a simplification complex that contains exactly the simplexes with balls of radius r intersecting. Right? And because you increase, as Bernhard suggested, the radii over and over again, right, the growing set of check complexes is called a filtration of the data set. Filtration of the data set. These check complexes are hard to compute, polynomial, but if n is the number of data points, right, you have n to the power of k plus 1 to compute the simplexes of dimension less than k. There are alternatives. They are harder to comprehend. This is why I focus on the check complex, but these other complexes are easier to compute. So what I do is, I build, if I analyze data, I build a so-called barcode. What the hell is the barcode? So I start with my data points and I fix a certain radius. Right? And then I observe, okay, here you have three connected components, A, B, C.